Okay, our next speaker is Anqi Li from MIT, who will speak on local properties of different sets. So please.
Thank you, Professor Nathanson, for the introduction and also for hosting this conference. So my project is local properties of different sets, and this is a project that did last summer at the Carnegie Combinatorics RU and is mentored by Professor Adam Scheffer. So what I'll be talking about today is kind of a brief history of the problem and its variants, and then we'll talk a little bit more about our specific results and proof ideas. So as an introduction to this problem, I want to talk about the general philosophy of this kind of problem and its variants, which is basically this idea of a local versus global paradigm. The general philosophy is basically that we want to understand a pretty big and complicated object, but we can study sub-objects fairly easily. And we want to be able to figure out what we can deduce from the information that we can gather from studying these small sub-objects about this big global object that we truly want to understand. So I guess one analogy to non-math is to MC Escher's art, where locally, in each scene locally, it is possible. But it's kind of this negative statement where even though locally we have something that's possible, globally this picture is just not sensible and doesn't make sense. So that's kind of the phenomenon that we're looking at, that locally we have some structure and whether we have the structure lifts to the global scale. So vaguely, the question that we want to study is what the local different set properties imply about global different set properties in the spirit of the paradigm that I mentioned earlier. And so I kind of need to unpack a little bit more in this statement, precisely I will introduce what different sets means and also what specific kinds of local global properties we're looking at. But before I go into that, I want to segue into talking about where this problem came from. And actually, I can throw out the orange phrase of different sets with edge colorings, which is the first kind of this problem that's been studied. So the problem is what the local properties of edge colorings imply about global properties of edge colorings. And Additive and Scheller first proposed this. So they were looking at what they call this quantity called FNKL, which is basically the minimum number of colors they need to color the edges of a complete graph Kn, with the local property that every complete graph on K vertices contains at least L colors. And so we have this really naive bound where F and KL is bounded above by n choose 2 because we can just give each edge a new color. So the question then is that we want to ask is that if we fix the asymptotic size of F and KL, so we know that it's bounded above by a quadratic, but suppose we fix the asymptotic size, what can we say about L in terms of K? So more specifically, the three kinds of threshold that we're interested in is what's the largest L such that F and KL is theta of n, and what's the smallest L so that F and KL is quadratic because we know it's bounded above by quadratic. And there's also a polynomial threshold, which is basically the smallest L for which we can find some exponent epsilon such that F and KL is theta of n to the epsilon. And so actually the first two, linear threshold and quadratic threshold, will resolve by addish. An interesting point of note is that the linear threshold and quadratic threshold only differ by 1. So that's kind of interesting. And more recently, the polynomial threshold was resolved by Collin, Fox, Lee, and Sudikoff. They found that F and KK is theta of n to the epsilon. So that is kind of background on the first kind of problem of its kind that was studied. But we want to go back to our problem, which is kind of an arithmetic variant of this graphical problem. So firstly, I want to describe what a different set is. So earlier we've seen some sets. So different set is kind of the same idea. We are looking at all pairs of possible differences between two elements of the set A. So as a silly example, if A is the set 1, 5, 10, 19, then the different set of A minus A is 4, 5, 9, 14, and 18. So we can make one quick observation, which is basically that if I give you a random set A, then we can kind of achieve the maximum possible size of a different set because we expect every possible difference to be different. So we have quadratic size of the set, number of differences. And for our minimum, we want to have as many overlaps as possible. So we'll take an arithmetic progression and then we get linear order of the size of the different set. So now we can phrase the question that I posed earlier a little more precisely. So earlier I was talking about local different set properties, and the natural one to look at that was suggested by Addition Schwartz was looking at G and KL, which is the minimum value of the size of different sets. Okay, so n refers to the size of the set A that we're looking at, such that for any subset A prime of this big set A, where the subset we're looking at has size k, so that's like the second parameter, we have that the difference set like spanned by A prime has size at least L. So like the local property is looking at the different set of a subset, and this is over all possible subsets. So earlier I mentioned that there was two bounds on the size of the different set. One is linear and one is quadratic. Quadratic corresponding to like a random set, and linear corresponding to like arithmetic progression. So like that carries over to like G and KL, because G and KL is talking about kind of like the size of different sets. So we know that G and KL is bounded below by linear and bounded above by quadratic. So when we achieve like linear, it basically means that we are taking arithmetic progression. And so like a little thought will convince you that G and K minus 1 is particularly referring to this case, where you have K numbers with K minus 1 differences. And so G and K minus 1 is n minus 1. And like on the other extreme end, when we want like the big set A to have all distinct differences and just 2 distinct differences, then like one way of getting that is we restrict in every possible subset of size K. We need there to be no repeats in differences. So G and K choose 2, where K choose 2 refers to the fact that we're looking at subsets of size K and they all have distinct differences. This guy is n choose 2. So one natural question to ask at this point is, what about like in between values? So we know like G and K minus 1, and we know G and K choose 2. So what about G and K, for example? Or like if we reduce K choose 2 by 1, so what if we look at G and K choose 2 minus 1, or like even G and K to the 1.33? What are these values? So we can ask similar questions as we did earlier, right? About like the graphical variant, we asked about like the linear, quadratic, and polynomial threshold. We can ask the same question in our case for the arithmetic variant. In our case, like the polynomial threshold is no longer relevant because we have the lower bound of linear and the upper bound of quadratic. So for us, the only relevant questions are like the linear threshold and the quadratic thresholds. And no thresholds were previously known for this problem. So to get a feel for how these thresholds work, we'll look at a couple more examples. The first I'll look at is GN33. Look at GN33 because GN32 is not very interesting, as we said earlier. GNK minus 1 is n minus 1 because it's an arithmetic progression effectively. So the local property here basically says that every subset of size 3 has to have a different set of size at least 3. And a little moment of thought will convince you that we're basically forbidding 3-term arithmetic progressions. So one way to get an upper bound on this set is to consider like Barron's construction that gives us basically a set of n integers that does not contain any 3-term arithmetic progressions from the set 1 to n times 2 to the c square log n. So what that basically means is that the maximum size of like my difference set is also bounded above by like n times 2 to the c square log n. So like GN33, which counts the size of this difference set, is bounded above by this factor as well. So it seems reasonable from this like upper bound to maybe guess that we can have like somewhat of a similar lower bound and that G and KK is superlinear. And yeah, so this kind of gives us like a feel for how like the linear threshold should look like. In fact, like it seems to suggest that the linear threshold is G and KK minus 1, which we know to be linear. And once we go from K minus 1 to K, it becomes superlinear. And the next example I want to look at is GN45. So just looking at GN45 because GN46 is boring because 6 is 4 choose 2. And as we have seen earlier, G and K choose 2 is n choose 2 because we need all our differences to basically be distinct. So here the local property specified by 4,5 basically means that for every subset of our big set A, that size 4 has to have different set of size at least 5. And so basically, because we have this like 4 choose 2 minus 1, we can allow for repetitions of differences in our set. But one observation that we can make that will be very useful for us is that if we have one repetition, so say A1 minus A2 equals A3 minus A4, then like assuming that our terms are sufficiently distinct, we can like kind of move our terms around and we can get another like difference. So one collision in differences gives us like another collision in differences. And so what this means is that in our like set of numbers that we're looking at, every difference has to repeat at most twice, because if a difference repeats, and particularly if a difference repeats twice, it has to be part of a 3-term arithmetic progression, because then otherwise we can just rearrange as seen in observation, And then we'll be able to get one more difference, but we can only have like one collision in differences. And actually using this idea, addition Shors managed to do some like counting and showed that GN45 is n choose 2 minus n plus 2. For us, like the precise values don't really matter, and we care more about the asymptotic. So like this suggests that there's actually like quite a big boundary from like k choose 2 that we can decrease it by a sufficient amount, and we can still get like quadratic growth. So it suggests that quadratic boundary might be more difficult to pin down as opposed to like the linear boundary. So now I'll talk briefly about our results. So as I alluded to earlier, we found that the linear threshold is k minus 1. So in particular, we showed that G and KK is superlinear. But before I talk about our quadratic bound, we will first prove an easy bound that will enlighten to as to why like our new bound is is an improvement of this easy bound. So in fact, I claim that G and K of 3k squared over 8 is on the order of like n squared. And the way to prove this proposition is to use kind of the trick that I talked about earlier, which I like to think of as switching endpoints. That if I give you a collision differences, then basically I can move the terms around and get another collision difference. So what this means in our context is that no difference can repeat more than k times, because otherwise we can find like k half pairs that have these repetition, and of these numbers, if we like do the switching endpoints trick for each pair of them, then we get like a grand total of k choose 2 minus 3k squared. Yeah, basically k choose 2 minus like the third parameter number of repetitions. And that's bad, because if you recall like what the G and KL means, it means that we can have at most like 3k squared over 8 minus 3k over 4 plus 2 we can have at most this number of repetitions, and we are like exceeding it. And so using the switching the endpoints trick, we do get that we cannot, that every difference can repeat at most like a constant number of times, and therefore we have the total number of differences being on the order of quadratic. So one question that we can ask is that, can we either improve the leading exponent? So can we lower like the fact that we're working with like L being quadratic, or can we improve like the coefficient from 3/8 to something better? So what we have shown is that we can improve 3/8 to like 17 over 64. And we can also like in certain case, well, in the case of improving the exponent, we didn't manage to be able to show that like to find the exact quadratic boundary. We found like something that's much weaker. It's of the form that of exponent 1 plus 1 over k minus 1. But we managed to like lower the exponent from k squared to k to the log base 2 of 3. So now I'll give some proof ideas for like the results that I mentioned earlier. So the first one is that for the linear threshold, actually this follows almost directly from like standard additive combinatorics tricks and well-known theorems, that because basically the linear threshold kind of relates to looking at arithmetic progressions. So we showed that if our difference set is literal of n, then A contains a k-term arithmetic progression. And given like this small difference set size, you can kind of biject vaguely like our set A to a dense set in a way that preserves arithmetic properties. And in this, because we know from Samaretti's theorem that if you have a dense set, then we can find arbitrary long arithmetic progressions. And these arbitrary long arithmetic progressions then contribute us to violating our local property of G and K. Yeah, like so this part was fairly straightforward, because linear thresholds has like, as I mentioned earlier examples, like a very intricate tie to arithmetic progressions, and it's much harder for us in the quadratic case. In fact, using probabilistic constructions via Feynman's theorem, we also like managed to prove like the following bound that kind of lies in the linear boundary. But I'll move on to the quadratic threshold, which is more interesting because it has structure that is not that moves beyond arithmetic progression. So it's kind of more oblique to the standard tricks and theorems from additive combinatorics. So one question we want to ask ourselves is that in the quadratic case, we kind of really want to pack together many differences. And one question we can ask is, how can we pack together many differences together compactly in a set? So I have a diagram over here that it's kind of like the Ramsey structure that we are trying to find in our set. Because we will use like kind of like a Ramsey-like argument, which is basically like we want to kind of stack the sets. We want to stack the differences together in a way that's kind of like periodic. As you can see, like we have, for example, units A1, A2, A3, A4, A5, A6, A7, A8. That's basically like repeated twice. And within each of like these two big units, I have two subunits, like A1, A2, A3, A4, that is repeated to A5, A6, A7, A8, and so forth. So like in this way, I can like pack a lot of difference repetitions together compactly and have a lot of repeating differences, which is good for us because then they can help us find sets. In our proof strategy, we can use this to find ways to violate our local structure. So the way to like formalize this is through energy arguments. And so the standard, we can think of like the standard difference energy as just encoding information of like repetition of one difference. So we can think of like this one difference, A1 minus A2 or A3 minus A4 as kind of a structure that this difference energy encodes. And so there has been generalizations of this standard difference energy into what is known as higher difference energies, where, for example, we consider like the difference instead of just repeating once, where we look at A1 minus A2 equals to A3 minus A4, then we look at this difference repeating multiple times. So for example, we can look at the 8 difference energy where like the structure repeats 4 times. So we have A1 minus A2 equals to A3 minus A4 equals A5 minus A6 equals A7 minus A8. And turns out that using this higher difference energy, we can get stronger, better bounds for like some of our theorems. So in our case, we introduced this idea of a structure energy. So as I mentioned earlier, we can think of like the standard difference energies as encoding like the structure of one particular difference. So in our case, we really want to look at, as I talked earlier about, this kind of like layered up Ramsey structure where we have a lot of differences built in together. So what we really want to do is to kind of take this structure where instead of just having one difference repeating, I want to have multiple differences repeating, and then I towel it multiple times. So for example, I can look at the following structure on the slide right now, and then I repeat it once more, and then I can look at this energy instead. And in fact, I can, instead of just looking at this repeating once, as we did in like, the case of normal energy, and then we generalize it to higher energy, we can also look at like higher structure energy, where instead of repeating the structure once, we repeat it multiple times. So it's the same idea as generalizing from normal energy to higher energy. So just like as a quick refresher, like standard difference energy basically like how energy arguments run is that the standard difference energy encodes information about additive structure. In fact, like a small difference set implies that we have a large difference energy. The converse is not necessarily true, but we do have this forward direction. And how that argument works as a quick refresher is that it works basically by Cauchy-Schwarz. Using Cauchy-Schwarz, we can reduce this basically to kind of a double counting argument and relate like information about the difference energy to size of a different set. And we get the bound that we want. So actually in the same spirit as this fundamental case, we can use iterated Cauchy-Schwarz and get the following analog for like our idea of higher difference energy, as I've shown you on the slide. And so why this is very nice is because it reduces questions about how large our difference set is to considering bounding this idea of our higher structure energy instead. So we just need to basically find an adequate bound for this difference energy. So one last step in our argument is that we reduce this idea of like, so first we made the first reduction of looking at finding size of difference set and reducing it to talking about energy. In our last step, we changed the idea of looking at energy into graph problem where we have a lot of results that we know that we can invoke. So the last step we built this structure energy graph where we basically connect the vertices of our graph are like tuples of numbers that is in our structure, and we connect 2 points of the graph if the tuples satisfy like the properties that we want in our structure. So like, for example, like if you look at the following picture that I took from one of the previous slides and we built the graph corresponding to it, then we have like we have like 1 point for like each of these 4. This is not a complete graph of all the possible like quadruples that we can find in the graph, but like for each of the 4 quadruples that I highlighted, we can build a vertex for each of them, and we'll connect all of them because they are all like part of the structure. But we also have like a lot of other vertices corresponding to, for example, A1, A2, A5, A6, and so forth. But for example, in this graph, like the fact that we have a complete graph kind of encodes the fact that we have a lot of repeating differences. So as I said earlier, we can kind of bound the size of like, so we can bound like the size of a different set in terms of energy. It turns out that we can also bound the size of like energy by the number of edges of a graph. Sorry, there was like errant like exponent of 2 on the slide. I shouldn't be here, but the size of the energy is actually given by the number of edges of the graph. So we basically converted our entire problem to counting the number of edges of a graph, subject to certain like subject to avoiding certain structures in our graph. And because this is a forbidden subgraph problem, there are a lot of results that we can invoke, and using this line of attack and avoiding specific forbidden subgraphs, we can obtain the 2 following theorems. The one about 17/64 that I mentioned earlier, and if you look at like even more generalized form of energy, we can get the second bound in the theorem below. The problem with the second bound is that because we generalize energy, we kind of need to weaken the global condition that we get. So we cannot get omega of n squared anymore. We can only get omega of n to the 8/5. But yeah, that is the end of my talk. Thank you for your attention.
So thank you very much. Are there any questions for our speaker? Let me just check the Q&A and the chat. No. So thank you very much again. We have a 30-minute break. The next